All right, we have a request for winter 19 test for part 2 roadmap. Just to be clear, this one's a lot bigger than yours is going to be. Let's do the start here, number 1. And you're saying, I don't know what this is, PCl5. I don't know. Oh, PCl5 right here. What does it do to an alcohol? It converts it to an alkyl chloride. What's it do to the stereo center? It flips it. That's all we need to know. Look at that. We learned from the test. So copy this with the, I'm going to put the CL on the wedge and the H on the dash, and that should do it, right? Oh, no. I might give you a different useful reaction that I want you to use. So, yeah. I might not use PCl5. I might find some other interesting reaction. And then I'm going to put the H on the dash. Hello, why'd you do that? Why did it stop drawing and do that? H and the CL on the wedge. That's a flip, right? And just a little, I use this over here to do that. And then what's going on here? It looks like oh, wow, there's some stuff that happened. Some new group came in on this position, not this position where the leaving group is. What's special about this position when it's one away from an alkene? It's got a category. This one's just secondary. This one's secondary allylic. So a secondary cation will happen if I have the right solvent. If you don't have a right solvent, this thing can't become a cation and then it can't rearrange. That's the story. Clearly, there's a rearrangement to make the cation be here. So you need an original cation. So don't give me everything that would lead to an SN2 reaction because that's not going to have a rearrangement, right? No carbocation in an SN2. So give me a nice solvent that will let this become a cation. What's your favorite protic solvent? Sure. The only issue is this thing won't dissolve in water, but this is not a lab class. You can pretend it works, right? Not a lab class. I typically like, whenever you want to use water, try to use an alcohol. And ethanol is a very popular solvent. And then your cation is going to occur, and now you just need a nucleophile. And there's a reason I'm choosing this nucleophile, the one with H on the sulfur and the ethyl. Because if I chose S minus, that means SN2 wants to happen. S minus is a strong nucleophile. So I want the moderate nucleophile. So I'm still on the SN1, SN2 Mabarth thing. And then I want SN1 to happen with that solvent. Then a cation happens and it rearranges to a better cation. Secondary allylic. Much better. That's about 3.5 degrees worth of stability. Did you know that? Some of you knew that. If you're allylic or benzylic, you add 1.5 degrees to the sign to predict the stability. So secondary becomes secondary allylic, which is like 3.5 degrees. Beautiful cation. What about HBr? That's an oldie but a goodie. HBr, no peroxide. And there's a big clue. Look. Take a look. Yeah. Ooh, I don't know what the heck happened there. That's wild. Anyway. Bromine on the Markovnikov addition. All right. So we got that. No double bond. Bromine here. Sulfur's up here still. Oh, I know what's going on now. I know what's going on now. This is a tertiary RX. Tertiary RX, but has a new. What does that mean? No.
Oh,
NGP. NGP. Little note here. This got to be an NGP. So if you're curious, mechanism-wise, you're going to get a square. Doesn't have to be a triangle. Did you know that? I don't have to show it. The product's already drawn for me. It's not like I have to predict the product here. That's a big relief. You say, thank you. Okay. I just need a O nucleophile because it's going to have to attack either this carbon or this carbon, and it's hard to get to the tertiary. It's blocked. That's secondary. So I just need a nucleophile, HOCH2CH3. Yeah, NGP. Yeah. What about this? Oh, I do want an SN2 in this one. Look, isn't that an SN2 product? Look, right? Backside attack on this carbon would give a nucleophile and a dash, right? So tell me the nucleophile, tell me a good solvent to make sure SN2 happens. Because your nucleophile doesn't make it happen. You know how I know? The nucleophile is this, O2 minus CCH3. That's acetate. It's a moderate nucleophile. So you got moderate and secondary. They both say, I don't know. Give me an SN2 solvent. I know you probably haven't reviewed them yet. There's 4 of them. Sorry? Okay, you can give me diethyl ether. I give you full credit. But there's actually 4 of them that really help the SN2. That one just slows down the SN1. You might have to wait a while for that reaction to work. It's okay. I give it to you. How about DMF? DMF stands for dimethylformamide. Well, you can do DMF, DMSO, acetone, or acetonitrile. That's the 4 that you have to learn anyway, that are called polar aprotic, and they are the cat's meow for SN2. It just means they're really good for SN2. Okay? Yeah.
So we don't have to draw it, we can just write DMF?
Yeah, you can write DMF. That's right. Now, this next one's an SN2 as well, but I don't know a nucleophile that has CH2 minus attached to NH2 for a good reason. It doesn't exist. You can't have a CH2 attached, CH2 minus attached to an NH2, and it needs to be a strong nucleophile. But up here, it tells us that if you use cyanide or have cyanide attached, it can be reduced to CH2NH2. And after you've studied chapter 9, you realize cyanide, the ion, is a strong nucleophile. And it puts a carbon where we need the carbon on a dash. And then you can reduce the C-triple-N to a CH2NH2 using the useful reaction. So I'm going to go like this. Step 1, KCN, comma, just use DMF again. You need an SN2. I can use DMF for the whole page for anytime I want to do an SN2, just so I'm not going to confuse you, I hope. It's already confusing enough. Now you've got to tell me how to reduce the C-triple-N to a CH2NH2. It's at the top of the page. Yeah, just copy it to H2 excess. Is that the first time I've used the short form for excess? I've used it before? Yeah, it's a phonetic short form, right? And PT. No surprise. That's like the chapter 6 reaction, isn't it? Except I have 2 pi bonds in a cyanide. That's why you need more than one H2. And then, oh, how do I add how do I add a Br to the less substituted carbon? Okay, HBr is needed regardless. Whether you're going to go Markovnikov for this one or anti-Markovnikov for this one, you need HBr in both cases. And you need a peroxide, and there's a reason why I'm going to draw it this way. I'm going to draw it this way for a good reason. And I'm going to put a triangle here because this is the same reaction right there. Look, HBr, a peroxide, yeah. CH3O taken twice means CH3O bonded to O bonded to CH3. There's OO in the middle. It's just a short way of drawing it and the heat. And you're gonna just, hey, you're gonna go like this. Dot, 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 O2CCH3 with an H. And there we go. And put the Br up here. There we go. Anti-Markovnikov, anti-Markovnikov.
Can you repeat again why you put, what's the role of the KCN?
It's a nucleophile to put this carbon on my carbon on the carbon with a leaving group. Step one does this.
Oh,
Step one makes this. See that? C triple N on a dash. Step two makes the C triple N into a CH2 NH2, which is what I want. Look, CH2 NH2. Okay. And then this one, hint, bicyclic. Whoa, 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 whoa. This is, I'm going to put it in quotes. This is a nucleophile. This is an X. I'm going to put it in quotes as NGP. Because that's how it goes. Oops. Not very clear. Light pink. You're basically going to draw the result of this. And you draw cyclohexane. Didn't change cyclohexane. You didn't change the methyl. You got a dash to a carbon that goes to an N with two H's on it. That goes to this carbon right here and has a plus. It's in quotes NGP because this is the end. The ring is the end. It doesn't pop open because it's not a strained ring. It looks a little strained, but its ring size is 5, isn't it? 1, 2, 3, 4, 5. That's not a bad ring. I know, this is hard. I agree. And what's going on here? That's a review reaction right there. Anti-Markovnikov alcohol from an alkene. Chapter 6 review reaction. 6.2. Anybody? Yeah. Hydroboration puts a boron on the less substituted carbon, which gets replaced with an oxygen by doing what? I give you half credit. Hydroxide and peroxide. Hydroxide and hydrogen peroxide. There you go. What's PCl5 going to do? Yeah, I'm going to put a, on the OH carbon, it's going to be a dash Cl. Because it does it tells us up here, it's going to flip the stereocenter. And dash Cl. Whoa, why'd you do that? Is that a bad spot on the screen? We've had those a couple times this semester. No, I just, oh, I look at, I changed the pen to draw. It's doing an SOS pen because we're in trouble. There we go. I didn't even know I did that. Dash, 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 dash. Dash, 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 Cl. And it's kind of the next level. So I would not be hard on yourself if this is not clicking at all. Try to pick off a few points to get. Like this one. I mean, that's just using the useful reaction right there. You could ignore everything leading up to this and still get the point for doing this, right? by just seeing it at the top of the screen, PCO5, say, PCO5, what to do, right? Eh, It's hard to assimilate all the information and know these reactions inside and out enough to do this. This is for the top notch students.
Oh, I'm not student.
I know you are.
Oh, I am. I'm not being foggy.
But the chat, you gotta have a challenge for everybody, right?
But there's too much. It's
The Kunta,
pretty fun.
is it? The Kunta?
Yeah.
Yeah. Tell him.
Awesome.
Kunta, there we go.
Yeah, you did. Honestly.
Okay. Good use of the word, huh? All right. So, hey, guys, this one I think we should be able to do. That's a strong new. That's azide. The only time we've ever seen azide. I know some of you haven't seen it yet because you didn't study the nucleophiles in chapter 9 yet. But this weekend, you're going to say, oh, it's on my list of strong nucleophiles, N3 minus. And yeah, I should be thinking about SN2 reactions with strong nucleophiles. So what are you going to do to an SN2 when the chloride's the leaving group? You're going to do a backside attack on it with N3 minus. And you're going to get a wedge to N3. And don't forget the acetate. O2CCH3. And that's got to become C triple C. Wow. That's a typo. There's a typo. This miraculously becomes a acetylide. I don't know about that. It's 2 points. Well, at least get 1 point for converting N3 to NH2 because that's right here. R attached to N3 can become R attached to NH2 using H2 excess and PT. At least get that point for me. H2 and PT. 1. And I think what I was driving at with the other one is I want an SN2 reaction. Although acetate's not a great leaving group at all. And what's my favorite SN2 solvent all day? DMF. There you go. This thing left. It got kicked off, backside attack. And then what about KNH2? Isn't that a strong base? Isn't this a terminal alkyne? This is synthesis from last test. Yeah, you're going to make a C minus and backside attack on allyl iodide. Please tell me how to draw allyl iodide. How many carbons? 3 with a double bond on the end. And the allyl carbons right here, got an iodide. So you're going to make C triple C minus. And hexane for another SN2 solvent, right? Not a great one. Backside attack, leaving group leaves. And there you go. Ali wants me to do a nice circle here. There he goes. R is attached to C triple C that has a new bond to a CH2, C double C. That's crazy. Yeah. And I don't know how the NH2 used to be trans to the methyl and now it's cis. And it's got to be a typo. There we go. But hey, isn't this the R group sticking off here now? Sorry, the R group's back here. And this is what's sticking off the R group here. That used to be C triple C, yeah? And then a C double, CH2, C double C. How do I get 2 BRs on the same carbon? That if I do BR2, I'll tell you what I get. Just playing what they call the devil's advocate here. Alkyne reacts twice. And CH2C. So it's not that one. Too many BRs. It's HBr. Yeah. Excess. And then this, I'm just gonna confess, this next part is goofy. But once again, there's a typo. But isn't this just getting rid of every BR and replacing it with pi? There's no pi's, and now all of a sudden I got 1, 2, 3, 4 pi's. That's 4 E2s. 4 E2s gives 4 pi's, right? Yeah, with glazed over looks, yeah. I understand. You need a strong base and heat. Just give me any strong base. Hit me. NaOH, KOH, sure. KOH and a ton of heat. Excess, you can write. I don't even need to see excess. KOH and heat.
So anyway, let's whenever I do this and see.
If you see halogens disappear and become alkenes, strong base and heat is your friend. Yeah, that's the E2. Or you could use the tert-butyl O- and no heat. Yeah. Okay. Wow. We're halfway there. Nice.
Oh, wow.
I know. Okay. Now we haven't done the other start yet. Have we successfully avoided the other start as much as we can? No. No. We didn't go this way, did we? CH2CHLI. What the heck? Acid-base chemistry on this molecule. Oh my goodness. What's the best? It's in the R group that you have to take an H now. There's no H's to be taken here. But in the R group, what's the best H? pKa 40. The amine is going to become an N minus. NH minus is attached to the and bing. It's the only change, right? There we go. And the N minus is going to do what? Oh, it's saying this zigzags up here. Hey, the N minus ends up attached to a carbon with a hydrogen and deuterium and a thing. And what? Oh my gosh, where'd this bromine come from? Oh boy. And how this double bond happen? There's too much. There's a lot going on. Can we worry about the SN2 first? Because isn't this a new bond from a nitrogen minus nucleophile to a carbon that wasn't there before? Isn't that SN2? So I need a carbon, 2 carbons actually, with a leaving group like a Cl. And I'm going to put the D on a wedge and the H on a dash. How come? How come? Backside attack, right? They're going to flip. That's SN2. Step 2. If I do this and say H2, comma, Lindlar's cat. What's that do? What's the only thing that reacts with H2 and Lindlar's cat? Alkyne. Yeah, the beauty of Lindlar's catalyst is it won't touch an alkene. And we don't want this lovely alkene that CH2CH touched. That's the same here. CH2CH. Didn't change. The triple bond did. It became a cis alkene. And now I need to make a bromine go in the position that's allylic to both this alkene and this alkene. Oh, allylic bromination. Talk to me. Initiation, propagation, termination. I'm linking everything into this question. Br2 and heat. Yeah. Gotta go with allylic bromination. Yeah, that's a lot.
In the box right before that one, there's a little plus 18.
Ethene, yeah, this becomes ethene.
Oh,
This is the conjugate base of ethene, and it becomes ethene. That's a hint that it was an acid-base reaction. That's why I put it there for you. That's the C- version of ethene, right? Yeah, and I think we have to go with the other start here now, don't we? Acetylene becomes a potassium acetylide, KEQ 10 to the 10. That means this is H2 in this box because it has a pKa of 35, correct? And 25 minus 35 is negative 10. 10 to the negative 10 is 10 to the 10 to the negative 10 is 10 to the 10. It's the only answer for that box. And what's going reagents? KH. Or just H minus. I'll take it. Oh, well, K's with my molecule. But you know, you can cross both K's off and then I don't care about K. Cross both K's off and I don't care about K anymore. All right, now we got a C minus nucleophile, isobutyl chloride. This is our first synthesis. And it is related to this stuff, guys. That's a strong nucleophile. This is a chapter 9 reaction. Yes, we did some chapter 9 stuff in chapter 7 when we learned about synthesis. It was called SN2. So you get your HC triple C with a new bond to what? What group? What group? It's the new bond to. It's in the right on the arrow there. Isobutyl. Oh, that's isopentyl. My bad. There's isobutyl. And hey, there's the isobutyl attached to an alkyne. How do I get another group on the other side? Start over. Acid base with H minus again, because you love H minus. And what's this new group that you're adding? I'm going to listen carefully to your answer and see if you've been learning the new stuff. It's a benzyl group. So you can use bromo attached to benzyl, which is CH2 and phenyl. Benzyl is like allele, but it's for phenyl versions instead of vinyl versions. And then it's review stuff. Syn addition of T, 2 T's. How about using something that's already on the screen? T2 and Lindlar's catalyst. How's that sound? Then how do you do the trans? Na, NT3. Oh, there's no T's on this one. NH3, like you said. This has no tritium. Trans 1-phenyl 5-methyl hex-2-ene would be this molecule, but now a double bond that's trans. And 1, 2, 3, 4, 5-methyl, yeah. So a lot of these review reactions aren't going to show up on yours. They're not. But, you know, it's good review. The end of the semester is also coming, right? So now you're going to take this alkene and hit it with some ozone, right? So the left part with 5 carbons will be this because that was a double bond. And the right part with, I can't read that. I think it say 6? I think it says 6. And that's, should be 8. Is it 8? Oh yeah, it should be 8, not 7. Then the phenyl, there, oh yeah. Yeah, the double bond got cut in half. So basically, think of this as now a double bond because that's what happened to get to here, right? And you make carbonyl on the right, left, and carbonyl on the right. So 1, 2 carbons, then phenyl. 1, 2 carbons, then phenyl. 1, 2, 3, 4 in a row. 1, 2, 3, 4 in a row with a 5th one. And that's the end of that story.
I like the side, I know the side.
We like the site.
So
Uh,
the toluene was just to get rid of the chloride, right?
The toluene was where? It's a solvent up there. Yeah, it's a SN2 solvent. It's non-polar. Yeah, it's just because that was the synthesis reactions are SN2. And then this one, 1-phenyl-5-methylhexane. Oh, I want both pi bonds gone. How do you do that? Replace them with H's. How? No, that'll just replace the 1 pi. I want to get rid of both. That's the original H2 PT that you learned. Yeah, that one will get rid of both pi's. And then 1-phenyl-5-methyl. There's the phenyl. There's a bromine on the benzylic position. How did you put a bromine on the allylic position? It was right. It was right. Where was bromine on the allylic position now? It was this crazy thing here. Yeah. Br2 and heat. It'll put it allylic or benzylic. Where are we? Where are we? A bromine on the benzylic position. Br2 and heat. We got to know our reactions. And 3 more boxes, and then we got to put this baby to rest. Oh, it's a secondary benzylic. Secondary benzylic. And a poor solvent, a poor new. That's also a polar product solvent. I can't read my poor there. Poorly written poor. P-O-O-R new. Polar product solvent. What are we talking about here? Why am I saying all these things? Heat just speeds up all reactions. Normally, you might start thinking about E2 with heat. I better say this with the microphone in front of me. But there's no strong base here at all. So the heat here doesn't help speed up the E2 reaction because there is no E2 reaction. Heat sometimes needed for reactions that are slow. And this would be slow because the poor nucleophile. So you just want to go SN1 major, E1 minor. You see the major and minors? When you see a lot of majors and minors, there's only 2 reactions we ever studied that had a lot of majors and minors. SN1 was the big one. And check out this morning's video. There was like 9 products. When you see 9 products, you just that's the SN1 one. I better do SN1. The other one would be E2. You can get multiple products there too. Okay? That has to be double bonds. And then this one, I can only make 2 of them. Cis and trans. So this one, I want the SN1 with methanol attached on the benzylic position where the bromine is. So OCH3 right here, OCH3, that's SN1. And then E1 minor, E1 minor. And they make double bonds. And you can go that way or this way. What's the difference? Cis and trans. There you go. All right, let's put this to rest. I know we didn't like this one. All right.